So here we have a question revolving around the factor theorem and remainder theorem. In part A, we are told that when we divide by x minus 1, in other words, when I put 1 into that equation, I should come out with the remainder of 8. So I get 9 plus 6 take 5 plus p should equal 8. Well, that will give me 10. When added to p, it should be 8. Therefore, p works out to be minus 2, as asked to show. For part B, well, we already know that x minus 1 cannot be a factor because it has a remainder. So I'm going to try x plus 1. Because it ends in a 2 here, then the tries would be for my first factor of 1, minus 1, 2, or minus 2. However, because we've got a 9x cubed, we could have a bracket involving a 3x plus a 1, a 3x minus 1, etc. So I'm going to try the x plus 1. So that means I am going to put into the value of x minus 1. So same setup as I did initially in part A, but with a minus 1 instead. Minus 1 cubed is minus 1 times 9 makes it minus 9. Minus 1 squared is 1 times 6 is 6. A minus times a minus makes that a plus 5, and take 2 is take 2. Now 9, or should I say minus 9, add the 6, add the 5, take the 2, actually does come out to be 0. Therefore, x plus 1 is a factor. Now I could get the other factors in this same fashion. However, because I know that that's one of the brackets, I should be able to get the remaining brackets. X times 9x squared will get the 9x cubed. 1 times minus 2 will get me the minus 2. The only awkward bit is how many x's I require in the middle. Well, 1 times 9x squared gives me 9x squared. I want 6x squareds. So when I times this quantity here, it must be minus 3x squareds, because 9 take 3 would get us the 6x squared. So there is the second bracket. Furthermore, when I come to factorise this quadratic, an initial guess, 9x squared, I'll write as 3x times 3x, and that does work, because if I write the 2 as 2 times 1, and I put that 2 as a minus 2, I'll get minus 6x. If I put that 1 as a plus 1, I'll get plus 3x, which will give us the minus 3x in the middle. So therefore, completely factorised, there's your 3 brackets.